Figure 12 shows the graph of a cubic curve. It intersects the axes at -5, 0, -2, 0, 1.5, 0, and 0, -30. Part I. Use the intersections with both axes to express the equation of the curve in a factorised form. So the fact that -5 is a root, that might tell me that x plus 5 is a factor from the factor theorem. If -5 is a root, then x plus 5 is a factor. Similarly, if -2 is a root, then x plus 2 is going to be a factor. And then if 1.5 is a root, or instead of writing 1.5, I prefer to write 3/2 as a fraction. If 3/2, which is the same thing as 1.5, if 3/2 is a root, then x minus 3/2 is a factor. So that might make me think that I could write my cubic curve for y as that. But let's just check that with the intercept on the y-axis as well. Let's just think about that. So it's going to intersect on the y-axis when x is 0. So if I made this 0, and this 0, then I would end up with just 5 times 2 times -3/2. So what would that give me? So the 5 times the 2 times the -3/2, that gives me -15, which is not correct. I shouldn't have -15. The intercept on the y-axis was -30. Therefore, my equation here isn't correct. I need to times this through by 2. It should be twice as big to give me -30 instead of -15. Now, this is now correct, but I could simplify it. I could write it in a simpler form because I could take this 2 and multiply this bracket here just to get rid of that fraction. The 2 times the x will be 2x. The 2 times the -3/2 will be just -3. So writing it like this will be better. So that's my answer for part I. I now need to show that that can be written like this. So I need to expand those brackets. So let's do that. I'm first going to expand the x plus 2 and the 2x minus 3. You can do this in any order you wish. So the x times the 2x is 2x squared. The x times the minus 3 is minus 3x. The x times the 2 times the 2x is 4x. The 2 times the minus 3 is minus 6. Collecting up those like terms, the minus 3x plus 4x is x. Now we're going to multiply everything by the x plus 5. X times 2x squared is 2x cubed. X times the x is x squared. X times the minus 6 is minus 6x. 5 times the 2x squared is 10x squared. 5 times the x is 5x. And 5 times the minus 6 is minus 30. Then let's finally collect up the like terms. So we've got the 2x cubed, which is by itself. We've then got the x squared plus 10x squared, which is 11x squared. We've then got the minus 6x plus 5x, which is minus x. And then we've got the minus 30 on the end. So we can see that we have now shown that the curve can be written in that form. Right, part III, or part 3. Draw the line y equals 5x plus 10 accurately onto the graph. So 5x plus 10, let me draw that on. So it's going to be a straight line. It's got a y-intercept of 10, so it's going to intersect here. and it's got a gradient of 5, which means I'm going to go along 1 square in the x-axis, and I'm going to move up 5 squares in the y-axis. So along 1, up 5, which takes me to about here. This is, that's gone up 5 there. Then along 1, up 5, and so on. It's going to look like this. So this is my graph of y equals 5x plus 10. Just continuing reading the question, I've drawn the line accurately. The curve and this line intersect at -2, 0. Yes, they do. I've shown that here. They intersect at -2, 0. Good, so I think I've drawn my graph correctly. It says, find graphically the x-coordinates of the other points of intersection. So I can see they are also going to intersect here and here. So what are those x-coordinates? Let me use the ruler to help me here. We've got the x-coordinate here, which I think is 1.9, roughly. And then I've got the x-coordinate here, which I think is minus 5.4, maybe minus 5.3, depending on how you've drawn it. I'm going to say minus 5.4. So I think from this, my 3 points of intersection are minus 5.4, the minus 2 that's given in the question, and the 1.9. Part IV. Show algebraically that the x-coordinates of the other points of intersection satisfy this quadratic equation. Hence, find the exact values of the x-coordinates of the other points of intersection. So it's talking about the points of intersection between my straight line and the curve. So we're thinking simultaneous equations between my cubic graph and the linear graph. So let's do some simultaneous equations. Let's take the cubic, the 2x cubed plus 11x squared minus x minus 30, and make that equal to the 5x plus 10. We're going to subtract the 5x from both sides. So the minus x take away the 5x is minus 6x. And we're going to subtract the 10 from both sides. So the 3 points of intersection will be the 3 solutions to this cubic equation. Now I know that x equals minus 2 is a solution to this equation. I know that's an exact solution to this. I know the other approximate solutions to this are the 1.9 and the minus 5.4, but I'm interested in the exact solutions here. I can use the fact that x equals minus 2 is an exact solution because that's telling me that x plus 2 is a factor of this. So I can now do a little bit of algebraic division to work out what the other factor would be. Factors, rather. So x plus 2 into 2x cubed plus 11x squared minus 6x minus 40. X into the 2x cubed goes 2x squared times. Let's multiply that out. The 2x squared times the x is 2x cubed. The 2x squared times the 2 is 4x squared, and we'll take that away. 2x squared take away, 2x cubed take away 2x cubed is 0. The 11x squared take away the 4x squared is 7x squared. The minus 6x take away, nothing is minus 6x. The minus 40 take away, nothing is minus 40. And we'll now repeat the process. X into 7x squared goes 7x times. 7x times x is 7x squared. 7x times 2 is 14x. And again, we'll take that away. 7x squared take away 7x squared is 0. The minus 6x minus 14x is minus 20x. And we've still got the minus 40 there. One last time now. The x into the minus 20. X goes minus 20 times. The minus 20 times x is minus 20x. And the minus 20 times 2 is minus 40. And when we take those away, we get 0. So what that's allowing us to do is to rewrite our cubic as x plus 2 times 2x squared plus 7x minus 20 equals 0. So the roots of this cubic are x plus 2 equals 0 that we know, or 2x squared plus 7x minus 20 equals 0. Which was what we needed to show. It now says, hence, find the exact values of the x coordinates of the other points of intersection. So we are now going to take this equation and solve it, this quadratic equation. I'm going to solve this by completing the square. You could, just double check. No, solutions relying on calculator technology are not acceptable. So yeah, I'm going to use completing the square to do this. So first thing I'm going to do is I'm going to divide everything through by 2. Does create this awkward 7 over 2 in the middle there, but that's fine. I need to do this to complete the square. So I've got the x squared plus 7 over 2x minus 10. Right, let's complete the square then. So we're going to half the 7 over 2 and get 7 over 4. We'll take away the 7 over 4 squared, which is 49 over 16. And we've still got the minus 10 there. The minus 10, I can think of that as being the same thing as minus 160 over 16, just so I've got a common denominator. This is the same thing as this. The minus 49 minus the 160 is minus 209. I can now add that to the other side. And square root. So for square root, I will get plus or minus the root 209, which I can't do, so I'll leave it like that. The root 16 I can, which is 4. Now I'll subtract the 7 over 4 from both sides, so I get x equals minus 7 over 4 plus or minus root 209 over 4, which I could write that with the single fraction as minus 7 plus or minus root 209. So those are the exact solutions to those points. So what I'm saying here, just to be absolutely clear, the minus 7 plus root 209 over 4, that's my exact version of the 1.9 where they intersected there. Whereas the minus 7 minus root 209 over 4. That's the same thing as that's the exact value of the minus 5.4, which was this point here.